Hello, my name is Adam Hines, and today I will be presenting our paper titled VPRTempo, a fast, temporally encoded spiking neural network for visual place recognition. This work is a collaborative effort with Peter Stratton, Michael Milford, and Tobias Fischer at the Queensland Centre for Robotics. Visual place recognition, or VPR for short, is a critical function in robotic localization, involving the matching of input query images to a database of recognized places, which can be challenging due to the dynamic nature of environments that are influenced by changes such as seasons or the weather. Traditional methods to perform VPR tasks often employ convolutional neural networks, which can be slow to train and deploy for real-time use. As an alternative strategy, spiking neural networks have garnered interest for VPR tasks, thanks to their low latency and energy efficiency, but have ultimately seen limited deployment. We introduce a novel spiking neural network for VPR that uses a temporal coding scheme where spike timing is a function of pixel intensity, allowing a single spike to convey up to 255 times more information than in rate-encoded systems. Using a simple 2x2 example, we see how pixel intensity through different inputs can determine the temporal code of a spike within a time step. This approach substantially reduced the necessary spikes to represent the same pixel data, improving spike efficiency by over 100%. Our network's architecture is composed of 3 layers: the input layer aligned with the image dimensions, sparsely connected to a feature layer, and a fully connected output layer where each neuron signifies a unique place. To improve both scalability and precision, we partitioned our network into expert modules, each responsible for non-overlapping sections of traversal datasets. Demonstrating the training regime, we first take raw input images, reduce the dimensionality, and patch normalize the pixel intensity to help keep our system lightweight. Then, the training phase involves 2 pivotal steps. Initially, connection weights between the input and feature layers are updated through spike timing-dependent plasticity learning rules. Subsequently, we apply a one-hot encoding and delta learning rule to train the feature to output layer, with each neuron learning a singular place. During deployment, we integrate all the layers, input the query images, and identify the neuron with the highest output as the corresponding match. Compared with the state-of-the-art spiking neural network system for VPR, our system learned an equivalent number of places in approximately 16% and less than 1% of the time when trained on CPU or GPU hardware, respectively. This increase in training speed highlights the potential for VPRTempo to be deployed to learn large-scale datasets. When comparing against state-of-the-art systems for overall performance, we see that our network performs comparably for precision at 100% recall with substantially reduced training and inference times, highlighting its suitability for deployment in real-time compute scenarios. Thank you for listening.